Alright, let's go. Count number of maximum bitwise OR subsets. Given integer nums, find the maximum possible bitwise OR of a subset of nums and return the number of empty non-empty subsets with the maximum bitwise OR. An array is a subset of an array B if A can be contained from B by deleting some possibly zero elements of B. Two subsets are considered different if indices of the elements chosen are different. Interesting. So like 2 actually is unique because they're different indices. The bitwise OR of an array is equal to the A0 or with A1 or with A whatever. So return the number of different non-empty subsets with the maximum bitwise OR. So nums 3, 1. 3 is 1, 1 in binary. 1 is 1. So the maximum bitwise OR is 3, is 1, 1. And you can have subsets that is 3 and 3, 1, I guess. Okay, here 2, 2, 2, maximum bitwise OR would be just 1, 0, which is 2. And there are 7 ways here. 1, 2, 3, and then there's 3 that's just 1, 1, 2, and 1, 2, 1, 2, and the first and last 2 is another 3, and then all 3 2s is another subset. So that's 7 different ways. And then here 3, 2, 1, 5. 5 is 1, 0, 1 in binary. So the bitwise OR would need to be 7, 1, 1, 1, 4 plus 2 plus 1 in binary. So you need the 5 to be part of any subset in order to have the rightmost bit be 1 or the leftmost bit be 1. So 5 must be there. 3 or 2 could be there. 1 doesn't really have to be there. So, okay, 5, 3, 5, 2, 5, and then 3, 1, 5, 2, 1, 5, 3, 2, 5, 3, 2, 1, 5. Okay. I guess I solved this at some point. Okay, let's see if I can't recreate some sort of solution. I think I first need to, so each value is between 1 and 10 to the 5th. 10 to the 5th is 10,000. 10 to the 3rd is 1,000. 10 to the 4th is 10,000, 100,000. I think I need to first what do I need to do? They don't actually say that you need to use mod here, even though there could be a pretty big number. I guess, okay, there's only 16 values. Otherwise it could be a pretty big set of combinations. I think I first need to figure out what the binary version of each number is. And how's this gonna work? So on something really simple like 222, 222 means that like if I have 2 in binary, it's 1, 0. And Actually, how do you denote binary? Denote binary number in Python. Is there a format for that? Like B? 0B? Directly denoted binary levels. Okay, so I'll just follow that convention. So in binary, this would be 1, 0. And if there's 3 2's in this, let's say there was X number of 2's. What is the count of the number of subsets that could be formed there? Like there's 3 2's, then it ends up being 7. 7 because it's 2 to the third minus 1. Yeah, I guess so. It's like so if it's 4 2's, then it'd be like 15. 2 to the fourth minus 1. 2 to the fourth because for each of the 2 it could be off or on, and there's going to be 2 to the fourth different ways of being off and on for each of the 2's, minus 1 for them being all off. So you can't have all the 2's be off, but at least one of the 2's be on. So at least one of the 2's be on. Okay. So where does that lead me? So for any bit, if I take the count of the number of values that has that bit, what does that give me? What if I'm dealing with something like 5, right? So if I have 5, which in binary is 1, 0, 1, if I were to also have, let's say, a 3, which in binary is going to be 1, 1, that means that either 5 or 3 needs to be there in order for the 1's place to be on. I can guarantee that 5 or 3 is going to be, or 5. So I'm trying to think of how to count the overlap. I guess there's really no. If I had some number 5's here and some number 3's here, I guess the 5's contribute the first bit, and the 3's contribute the second bit. They're kind of independent. Because I would need to have at least one 5, and we need to have at least one 3. And having at least one 5 or at least one 3 gives me at least one of the last bit. What if they were non-independent? Like I had a 7, I guess. Which is 1, 1, 1 in binary. So how would I count the number of ways? If you find the maximum possible bitwise-OR the subset, turn the number of different ways that maximum can be obtained. So if you have a 7, then that 7 makes the bitwise max be 7 as well. be what if you, like if you looked at the least common bit, then there's still so many dependent bits based on that, possibly. Get entry array, find the maximum possible Bitwise-OR. The subset number of non-empty subsets. Yeah. I feel like maybe I should maybe I can I ignore the duplicate somehow? Like if I had multiple 3s and multiple 5s, multiple 7s, and the 2s, is there a way to me to ignore the multiplicity of that value? So the number of ways that you can have at least one of that value is 2 to the frequency minus 1. The number of ways you can have that particular value is 2 to the frequency minus 1. If the frequency is 1, then it's just one way of having that value. 2 to the first minus 1. And then if you don't, so for any value, for any bit, if you have two different values that can generate a 1 in that bit, they each have their own multiplicity. But then when you have one of them, it also could guarantee bits elsewhere in the overall scheme of things. How to logically, how to consistently count everything. So for every bit, what happens? This doesn't feel like a binary search way. And I wonder if this is like a, I wonder if I should be able to use backtracking for this one. Backtracking or dynamic programming. I wonder. Dynamic programming. So what would be the recursion there? So if you have 16 values, 16 different values. So you could include a value. Could include a value in some array of values and move on to the next value. Branch it. No, backtracking wouldn't work, right? There'd possibly be like 2 to the 16th different paths that you have to backtrack through. I think for each value of the 16 values, you look to see whether or not you include that value, move forward to the next index, and then move forward, all the way to the end. Generate whether or not you generate the number of ways that occurred. Three, 1. You have 1, 1. So you need to have 3. And the number of ways that you can have a 3 is 1. And the number of ways that you can have, because the 3 has to be there, so there can't be 0 3s. And then the 1 is completely optional at that point. So there's two different ways you can have the 1. So it's 1 times 2 is 2. Here it'd be 2, you have to have the 2, so it'd be 2 to the 3rd minus 1, which is 7. Here, you need to have the 5, so it's one way of doing that. And you either have the 3 or the 2, so there's 2 ways of doing that. I think. No, it's actually 3, 2, 3, 2. So I guess there's 3 ways of doing that. So 1 times 3, and then the 1 can, or the 1 doesn't need to be there. So times 2, 1 times 3 times 2. Yeah, this seems so off. So the 5 guarantees the 1. 5 guarantees the 1 bit to be available. What is the logic? How would I consistently say that based on the 5 being there? I wonder if I can so for each bit, okay, so how many bits are we dealing with here? 10 to the 5th is the value. So I put it in, that's 10 to the 3rd is 1,000. So I put 100,000. And binary is what? 1, 2, 3. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 17 bits. That's 9, 12, 17 bits. So I can go through each of the 17 bits and see which numbers can contribute to it. See which numbers can contribute to that bit. And some numbers can contribute to multiple, or most of the numbers probably contribute to multiple bits. Multiple numbers contribute to multiple bits. And a number of ways to reach every possible bit. The number of ways to reach every possible bit. Every possible of the 17, possibly. So if you do what? Hmm. 17 bits. I don't think guessing the number would be correct. Like, it's not like a binary search for the correct number. I almost treat the numbers as a random collection of bits that they turn on. So sorting it doesn't really do anything. 3, 5, 3, 2, 1, 5. Five is the only one that is possible for one of the bits. So it has to be there. And then you can guarantee that the other bit is there based on it. 5 being there makes the 1's bit there. So, but then that's not really the tricky part. The trickiest part is how you tell based on bits that have multiple values, none of which are individually required. Like the 3 and the 2, they can both be the second bit. If the 3 is picked, then in theory it could be generating the 1's bit. But then if the 2 is picked, then it doesn't generate the 1's bit. Huh. Find the maximum possible bitwise OR. subset of nums returns the number not empty. We have to do two subsets. Okay. First thing I should probably do is just find like the counts, maybe, because that's really what's necessary. It's really the basis of the calculation, I think. So you have your unique values in the nums array. Each unique value has some bits that turns on. Each unique value has some bits that turns on. And then what? I wonder if you can do backtracking here. I feel like that's there would be too many paths. There would be 2 to 16 possible different paths of which values include or don't include in the array. Three, two, 1, 5. If you start with your most restricted bit, if you ignore the 5, it would be 3 and 2. And at which point would be you would either need the 3 or the 2 and 1. The 2 and 1 would Bitwise-OR to 3. So it'd be like 3, 2, 1, 3, 2, 3, 1, 3, 2, 1. So it'd be 1, 2, 3, 2, 1, 3, 2, 3, 1, 3, 2, 1. So 5. So if you pick 3, then you'd have 2, either the 1 or 0. Pick the 2, and you also have 2, and you have 1 or 0. You have the 1 with not the 1. So it's 4 total, and then you have the 1 that includes both 3 and the 2 and the 1. That's a bad calculation. 3 includes 1 or 0. So you have 3, you have the 2, number of possible ways to get you have your 3, you have your 2. 6 subsets. Out of, I guess there's 2 to the 4th minus 1, not completely empty subsets. 3, 2, 4, 5. Plus 15 possible different combinations, or 15 different possible groups, subsets. And you got 6, 3, 2, 1, 5. What if you what in my distant past have I learned that would solve this? And I probably didn't make a graph from this time. Or did I make some sort of search? Some queue? Push the 5 on. If you know you have a 5, then three, 2, 1, 5. Push the biggest number on. Push the biggest number on, then the rightmost bit will be there. Guess if you don't have the biggest number on, then the rightmost bit might not be there. So if you start with the rightmost bit, then either the biggest number is there or a number big enough so that that bit is there. And there's just branching paths. So many possible branching paths. So reverse sort, take the biggest number, take the biggest number, add that number to the list, move on to the next number, add that number to the list, maybe. It could be optional or it could not be. I wonder, what if you tried to do like the most minimal set? So let's say you include the biggest number, and then you try to find the most minimal set of bits after that. Would that work? So you're trying to guarantee that your rightmost value, your largest value is included. You then move on to the next bit that is not necessarily included. And then you include a value that, the largest value that turns that bit on. And then you move on to the next bit that is not guaranteed. and then you do, and when you reach the end, you add back in the number of ways to fill in the rest. And that'll be one pass. And then you go back, turn off the biggest bit, and then turn on the next, or turn off the biggest value, turn on the next biggest value. And you can guarantee that the difference between the two counts is your biggest value is not there. Does that work? So you start with your biggest value being on, and then you move to the next bit that is not guaranteed to be on, and then for each value that could turn that bit on, you have to go through them one by one, I think. So like turn on 5, then you turn on 3. Yeah, so 5 has to be there. So the next bit that is not there is the 2's bit. So you start with 3 being on, and at that point that covers all the bits. So 1 or 0, 1 or 0, or 1 can be on or off, 2 can be on or off. So 1 or 1 on off, 2 on off. That means that there's 4 ways of doing that. And then next is 5 can go to 2, which can go to 1 being on off. So that's 2 ways. So 6 ways total. So for each bit, you do a pass. You have to do a pass for that bit. Each bit for each value. Is that fast enough? 5, 3, 5. So each value, what is the speed of said? There's only 16 bits, or 17 bits. And when you turn on the value, then that turns on at least 1 bit. And then you move down to the next available, or the next non-guaranteed bit. And that would that's guaranteed to, what is the speed of this? I think this might be 16 times 16 speed, maybe, because each pass 16 There's 17 bits, 16 values. So you can start off with any of the 16 values, and when you do those 16 values, it needs to move downwards 1. So I guess this is 16 squared. 16 times 17. Okay. So, I don't know. Okay, so I guess I probably need to start by doing some sort of sort here. Values is going to be counts.keys. Values.sort reverse equals true. Alright, let's go ahead and see if this thing is doing what I think. I guess values is a dictionary key. Is it really? Counts. Oh, I see. Value equals sorted counts.key. Counts.key gives you an actually, I'm not sure why that didn't work. Values. Okay, so I have uniques is that, in reverse order is that. So then I need to quickly translate the number to some binary. Quickly translate each number into some binary. So what would it mean for each number? I need to figure out for each bit, maybe the values that are for each bit, the values that turn on that bit. Okay, so maybe I have a bit dictionary or a bit2d array. Bit contribute. Bit array. Let's go ahead and make this a dictionary of list, default dictionary. I feel like it should just be an array of lists of size, whatever the biggest number of bits is. 5 is 3. 5 is 3 because 2 to the third minus 2 to the third is 8. I think it should be something like list for k in range. So 5 is going to be 3. Integer of log 2. Binary log Python. Well, I should try and memorize this. So log2, math.log2, the number. Log2 of the largest number in values. I think. Not right. A single list. Oh, is it +1? So 8 log 2 of 8 is going to be log base 2 of 8 is going to be 3. So I want 4. If it's value is 1, log base 2, 1 is 0, but 1, 1, so I think it's +1. Okay. One's place in the two's place. One's place, two place. One's place, two's place, and the four's place. Okay. So for every value, I need to figure out which list it adds on to. For every value, five. So how I do it? I take while the value is greater than 0, while the value is greater than while the value is greater than 1. It should be better with this bitwise stuff. I think I take the remainder of the value, subtract it, and divide the value by 2 to do basically a shifted value. Yeah. If the bit of x left by y places, new bits are introduced. Num shifted to bitwise right shift. X shift bitwise shift y returns x with the bits shifted to left by y places. Yeah, so how did I learn this before? It was like do a bitwise, I think it was x bitwise and with 1. Each bit of the output is yeah, I think this should have been something like while value is greater than 0, the bit is equal to value and 1. No, this is OR. And does a bitwise and. So that gives me the leftmost bit of it. The leftmost bit of it. At that point, I want to do bit array if the bit is there. Then bit array of some index. Append this value. This index should start with index 0. And then index plus 1 here. I think that's right. Okay, and then I need to do a bitwise shift of the value. So value shifted over and I think it's like left 1. I think it should be something like that. Yeah, let's see how this goes. That's actually what I was hoping for, huh? Okay, this is not it. Yeah. I guess the original is needs to be added to the thing rather than the shift value. Maybe for me to say each unique value and values, let's say the value is currently the unique. And then append the unique. Okay, so this is kind of what I was thinking in my head. Thought maybe in reverse fashion, but it's fine. So, yeah, still not really, but fine. Go ahead and just do bit array equals bit array reversed. Okay, so there's the 2's and there's the 1's. The things that generate a bit in the 2 spot is 3. The things that generate a bit in the 1 spot is 3 and the 1. Things that generate a 2. Things that generate something in the 2's place is just 2. Generate in the 4's place is the 5. In the 2's place is 3 and 2. In the 1's place is 5, 3 and 1. So that's fine. Okay. So then I go through each okay, and then go through each index a bit, and then I keep track of the unique values that I have, I guess. Okay. For every, so this is kind of like, so I'm going through this and also this, so maybe this is like a two-pointer deal. Two pointers, one for the values and one for the bit. So for every value index in range of the number of values, where the number of values is equal to the length of values. So for every starting value index, what am I thinking of here? So for every starting value index, I'm going to first consider having that part of my group of things. Part of group of things. So how would you count that? So if I think about 5 in there, so maybe an included set. So value is equal to the values at this value index. I guess included should start with this value. Should it be a set or should it be like a list? Does it matter? Maybe. Probably a set. Probably need to find a way to quickly identify whether or not something is included within the included set. So for every value, so at this value index, I need to actually, what is this going to do? This seems like it'd be nested for loops, so this seems to be like recursion actually. This seems to be like recursion. So I need to go through each index in turn. And then for each index, go through each successive index. So this does seem like backtracking, but then backtracking with 16 possible spots at most. And it does seem to go faster, so 16 factorial. So what is 16 factorial? Oh boy, that's a huge number. Oh boy. Is it really that big? 16 factorial? I guess 16 is at least 10 to the 6th, or approximately 10 to the 16th. This does seem to be recursion, where I recurse to the next index. So I need to go through 5, and then 3 it needs to loop through 3 and 2, and then it might need to loop through other stuff. So I can't really define how many times it loops. I can tell what it does at each loop, kind of, which is see what's available at that loop, that index, go through each possibility. Okay. Let's go ahead and call backtrack here. Index. Guess I pass in an included set, maybe. Oh boy. So this thing's gonna call like answer equals backtrack go. Index starts with 0. It should pass in the value set, the included set. And yeah, and the included set is initially just empty. Okay. Right, so let's do the base case here. If the index is equal to the last index, which is the length of the number of values. So index starts with 0, 0, 1, 2, 3, 4. Then what would it do? It would look through, it would count the number of ways to do the included stuff. So the count should be equal to based on what is included and based on having at least one of each included value and any number of the non-included values. So for every, so I guess I should start with count as 0. Count as 0, count as 1. You can actually count as 1 for every included, for every value included. So let's say that there are 3 5s, and you need to have at least 1 5, so I think it's going to be something like value times equals 2 to the power of the counts of the value minus 1. So if there are 3 5s, then there's 7 ways of getting 1 of the 5s. And if there's 2 3s, there would be 3 ways of getting 3. Yeah, I think that's right. Actually, I probably need to actually iterate over every value. So for every value in values, if that value is included, else it could be there, it could not be there, it doesn't really matter. So I think that's just the 2 to the power of the counts of the value. Yeah. I have no confidence in this code being anything close to be incorrect. But it is what it is. Okay, so that's the base case. So if your index is at the end of the values that you're trying to consider, it also needs to be including the bit that you're dealing with. So there should be an index and there should be a bitdex. Zero zero. So if you're on the first bit, so let's see. So does it end when the bitdex is at the end, or does it end when your index is at the end? So there's a value index I'm thinking of. It's going through these, and there's a bit index that you can think of that goes through these. Actually, maybe it's the bit index that should be. But then the bit index doesn't go through the number of values. I guess I really don't need to go through all the values themselves. Yeah, I guess this should be the bit index that is equal to the end. So the bit index is equal to numbers of bits. It's the length of bit array. So if the bit index is equal to the number of bits. Count is 1. Oh, whoops, what am I doing here? Count is equal times equals. Count based on having at least one of each included index, include value. I think that's what I'm thinking of. Okay. So the bitdex goes down. Okay. So then the backtrack would go here. So if I'm at the start, then I'm going to go through each value in the array at this spot. So in each value, so I guess maybe I can do a simple trivial case where if there is no values in this spot, then it doesn't really matter. So if the length of if the length of the length of the number of values at this spot. Bit array at this bit index is equal to 0. Then move on to the next one. Return backtrack. Index still is the same. bitdex is going to be 1 larger, included is still the same. Okay. Okay, if the length of the bit array, okay, then otherwise there are values at the spot that I need to consider. So for every value in the bit array, this spot, if the value is included already, and continue. And continue? What does continue mean? Value bit array. I guess I need to sum. I need to do a sum, a partial sum here. Included, and that means sum, or so there's partial sum is going to be plus equals backtrack same index. How does my indexing here work, actually? I wonder if I need to actually have the. I wonder if I need to actually have this index, since that index. Does it reset? Does it even matter? Because I have to go through these. I don't skip these, right? Go through every single one. If it's not already included, then I include it and then move on to the next. Include it and move on to the next. I don't know if I need this other index. Okay, I'll just ignore it for now. Bitdex included. So for every value included, then so now if the value is already included, then I need to move on to the next index, because it doesn't really matter for this one. Otherwise, if it's not included, value. So actually, let me think about this. So I'm at a certain bit spot. So my included is 5, and at bit spot 1, I want to go through 3 and 2. 3 and 2 would be bit array at 1. So I would do 3. 3 is not included. But if there was a 5, then I would just skip this spot. There was a 5, which is the biggest thing, then I would skip it. And then if there was, said there wasn't a 5, but there was a 3, then I would also skip for every value in bit array at this bit index. If the value, first need to see if all the values are not part of the included array. So the included has any of these values. And that should mean the bit array is there. And if that should mean bit is already there. Because the 3 is not there. So I should be able to break. I should be able to say that if any of the biggest numbers are there, then I should be able to break, because that means that this spot has already been included. If none of the big numbers are there, then every number that is there should be attempted. So like if there was because there's no 5 in this set, then that means the 5, this bit hasn't been generated. So I need to iterate through 3 and 2. If there was a 5, then I need to not do any of this stuff. Like if there was a 5 here, then I don't do 3 and 1 at all. So what is the logic there? For every value in the bit array at this index, if it's included already, then I need to break immediately. I guess breaking immediately would just be returning or iterating, recursing to the next one, and returning that recursion. So if the value says included, then return backtrack index bit index plus 1 included. And then if it isn't, because this is doing the largest, actually, let me think about that. So let's say there was another number here. Let's say there was a 3, 2, say there was a 6. Let's say 6 wasn't included. Say 6 wasn't included somewhere before it. So the 5 is there. But what if the 5 wasn't there, but there was a 4? 5 wasn't there. No, let's say there was a 6 and a 5. 5. So I'm looking at the largest thing that generates this bit. But even if the largest thing should be if any of the things is there. Yeah. It needs to be if any of the included stuff is already at this bit. Then return immediately. Yeah, if any, it includes this bit. Doesn't seem to be very fast though. Because then you have to do a set lookup each time, or set comparison of the values here versus the value included. You don't really leverage the fact that the values are in decreasing order. So if you have a value index, the value index is limiting the things that you're considering. Value index is limiting the things that you're considering. Five. Maybe when I add the 5, I should be adding bit values. So the 5 adds is the 4-bit and the 1's bit. And then I go through for the 5 toggles. 5 toggles on. 5 toggles on 4 and the 1. And then I go through each bit that is not toggled on. Five is linked to 0 and 2. When I add the 5, I turn on 0 and 2 bit as part of it. And then I go on to the next one. If that next one is already if the bit is not already on, then I do the iteration of the values at that spot. And I keep track of it. Maybe. Oh. 5 turns on bit index 2, bit index 0. Turns on bit index 1 and index 0. When 3 turns on bit index 1, it could already be there, or index 0 could already be there. So how would it know when it reverses it? How would it know when it reverses it? 3 turns on bit index 2, bit index 0, 2, oh, 3 turns on bit index 1 and bit index 0. Bit index 1 was already there, was already on. So when 3 backtracks. I'm not going to be able to, or shouldn't be, removing bit index 0. It's easiest. 3, 2, 1, 5. That's my idea originally. 5 goes to 3, goes to 1 and 2. 5 is on, so it goes to the next index. Then let's say you have something really large. So at each index it goes to, something has to turn on at that spot. At each index it goes to, either it's already on, or it needs to add some additional value to turn it on. So when 5 goes to the next index, that spot is not on, so it needs to add either the 3 or the 2. When it adds either the 3 or 2, it needs to turn on whatever bits elsewhere that value implies. And then it moves on to the next bit. Five turns on bit second bit, 0 bit. And then it moves on to the first bit. First bit can do 3, which turns on bit 1, or 2, which doesn't turn the first, but the 3 has already turned, 5 has already turned on that first bit, the rightmost bit. So when 3 backtracks and removes itself, when 3 backtracks and remove itself, then what? I guess you could actually keep track of a 2D array instead. 2D array of includes both five would go through each spot where it turns on a bit, and then the 3 would go through each spot where it turns on a bit, and then when it undoes itself, it goes through each spot where it turns on a bit and removes itself from the list at that spot. Removes itself from the list at that spot. Alright, I need to take a break.